This week in this chapter we will discuss about diodes. So in order to cover uh, not completely but sufficiently on diodes, we will discuss the content will cover three things. The first one is to cover the construction of PN junction, which is the base that make a semiconductor diode. And then secondly, in the chapter we will also cover the and be familiarized with the diode equation and the characteristics, the equation and its current and voltage characteristics. And then finally, we will try to look into application circuits that use diodes, right, and analyze them, analyze these various circuits where the semiconductor diodes are used. So basically, there are two types of circuit. The first one we look into a simple circuit utilizing diode, and then in second part we will see what we call a rectifier, which are divided into two: half wave and full wave rectifier. So let's start this chapter. Before we start, we'll look into the background of diode. So sometimes we get curious about the word diode. The term diode itself has been used for the first time by William Henry Eccles in 1919. So this is a picture of William Henry Eccles. Basically, he is one of the pioneer in the radio communication technology. And what he used was, at the moment, it wasn't the diode that as we have today. It was a glass tube, vacuum tube with a cathode and anode. So he called it diode. And since two poles component that have cathode and anode are called diode, right? So what does diode means? Diode is come from Greek words di and ode. Di means two, ode means electrode, right? So and the electrodes are called anode and cathode. So that's a bit of background on the terms diode. So where do we use diode today? So there are a lot of types of diode. There's many type of diodes, right? So here I list several examples that we are probably familiar with, where we can see them in daily applications. So the first one is the light emitting diode, or LED. So we've seen this in displays, in signals like the traffic lights, in illumination for decoration, and even in television. So this is a sample of the LED technology used in our television, right? And the second one that is used a lot is photodiodes. So photodiodes, what is it? It is a kind of diode that used as light detectors. So this is a sample of photodiodes. It is sensitive towards photons, basically towards light. It receives lights and it will react to that light. So it's used in light detectors, right? So we have many light detectors today that operates probably our home intelligently, and we also use it in sensors, for example, in communication. And finally, the thing that all of your lecturers are familiar with is the laser pointer. So in a laser pointer, what they have inside it, some of them have what they call a laser diode. So they use as pointers, and they use also as security alarm. So as you've seen in movies where there are lasers in front of a safety safe, for example, that is basically laser diode used in a security alarm system. So what is the basic component behind diodes? How does it constructed? How do we construct a diode? So a diode is basically a PN junction. So it's a material that is formed, a PN junction is formed using a semiconductor material. So what is a semiconductor material? A semiconductor material is basically a material that have 4 valence electrons. If you remember, 4 valence electrons means it has 4 electrons at the highest level of energy at the most outer circuit of its electron. It has 4 electrons, right? So P and N are different materials. One is P, one is N. So right, about semiconductor materials. In periodic table, if you want to look for semiconductor materials, there are materials basically that has conductivity, I would say, in the middle. So those who are in red in this periodic table, The one that is marked in red are basically the one that have a very high electrical conductivity. So electrical conductivity in Siemens per meter. It shows how much, how easy does that component or does that element conduct electricity. So for example, we can see here in very dark red, we see copper, we see silver, and our room is basically it's gold. So these three elements along with aluminium conduct electricity extremely good, right? And there are other components in blue or in light yellow. Those are the components that doesn't conduct electricity at all, right? It is dielectric basically. So and then we have also the component that is in the middle, around in orange color. So basically here is the component in this line is the component with 4 valence electron, and the components that we're using the most for semiconductors is Si and Ge, which is silicium and germanium, right? So the semiconductor material, this silicium and silica and germanium, what do we do with them? What do we do if basically they have initially the silicium. For example, we take an example of silicium. Silicium has basically at the beginning 4 valence electron, which are stables. What we do with them is basically we dope them. I mean, we inject them with impurities. The impurities being boron or phosphorus. So depending on which impurities you introduce into the semiconductor, you will create either a P material, a P region, or N region. If you look here, basically if we inject a boron, boron is basically a material with 3 valence electron. When it is injected into the semiconductor, what it creates is basically it creates a free space where an electron can move in. So this free space is what we call holes. So by injecting boron into silicium, into semiconductor, we create a p-type. So we create a holes where electron can move in. That's what we call a p-type. On the other hand, when we inject it with phosphorus, phosphorus basically has 5 valence electron. When we inject with 5 valence electron, what we create is we create a free electron that can move around, right? That can be transferred across the material. So when we have an extra electron, a free moving electron, that's what we call N-type. So N-type with free moving electrons, P-type with a moving holes. We call it holes because we have less electron. But again, of course, these two materials, P or N region, are both neutral. It's just that they have holes, or either in N-type they have extra electrons. So P with extra holes and N with extra or free electron that can circulate. Right. So what is the working principle of a diode? Diode is basically a combination of N-type and P-type. So what we create is, in the middle is what we call PN or NP junction, right? The free electron basically from the N-type will move to the junction to try to fill in the holes on the P-type, right? As they fill in the junction, what they create is they create this region where the holes, there's no more holes in the middle region. This region on the junction of the P and N type material is what we call depletion region, right? This depletion region creates a barrier potential that oppose basically further migration of N to P. So as this electron moves into holes near the junction, it creates the barrier, and this barrier creates a barrier potential. So this barrier potential is very important in diode. In diode, it creates a characteristic that we keep using after this. So let's see. So a diode, how does it work? It works in two conditions. It can work either in what we call forward bias or reverse bias. So what is forward bias? A forward bias is when we connect a voltage supply in this configuration. So what does it mean? It means that we connect the anode or the positive, the p-type junction with the positive terminal of a power supply, and the negative, the n-type junction with the negative terminal of our supply. This is what we call forward bias. In forward bias, what happens is the voltage, the electrons from our power supply will circulate into the p-type junction, right? Into the p-type junction, and will try to cross the PN junction. When they try to cross the PN junction, as previously mentioned, we have a barrier potential, right? We have barrier potential. The current can only pass the barrier if the voltage that we supply to the diode is larger than the barrier voltage. So this voltage that we need to overcome is what we call a forward bias voltage. A forward bias voltage. So a diode have a forward bias voltage. So what's the level, what's the amplitude of the voltage that we need in order to make the current go through a diode in forward bias? The voltage, well, it depends on the material of our semiconductor. Just right now, I've mentioned there's two type of semiconductor materials that we use a lot, either silicium or germanium. So at least if we construct our PN junction using silicium, we will have a bias voltage of 0.7 volts, and if we have germanium, we use germanium, we would have bias voltage of 0.3 volts, right? So it means that in order to be able to conduct currents, we have to at least the voltage that we're supplying has to be larger than 0.7 or 0.3. Okay, so basically a remark can also be made here. In this circuit, basically we only have diode connected to power supply. So for the circuit above, once the voltage supplied is larger than the bias voltage, the circuit is closed. Circuit is closed means the diode now conduct the current. It becomes just like a conductor without any resistance. If there is no resistance, then we can imagine that the electron that come out from the positive terminal of the power supply goes directly into the negative terminal of the power supply without any resistance. It means we're creating a short circuit. So that's not what we want to create, because we don't want to damage our power supply. So basically what we do is we add a resistance. So if I can change into a pen. So basically what we do is we add a small resistance to make sure that a short circuit will not happen, right? So a resistance is needed to limit the level of our current. And then in opposite direction, if we connect now, let me get my pointer. So if you connect now in opposite direction our power supply, where we have our positive terminal connected to n-type and n-type junction, and the negative terminal connected to the p-type junction, what will happen is that this is what we call connection in reverse bias. If it is connected in reverse bias, the free electron in n-type will go to the positive terminal of the battery, and the same goes for the holes in the p-type, goes to the negative terminals of our power supply, thus creating a larger barrier potential. So we create larger barrier potential. So the area where we have barrier potential is what we call the depletion layer. So the depletion layer increase, therefore the current will never be able to pass, except for very minority charges that we call minority charge, right? So if it is connected in reverse bias, the current will never be able to goes across the diode, right? So from that explanation of the basic the basic of PN junction and the behavior of that PN junction that creates that bias voltage, we can therefore deduce a characteristic of a diode. So here we have a symbol of a diode. So the anode is noted as positive terminal and the cathode as negative terminal, and we show the direction on which it is forward biased by the direction of the arrow, where it will conduct current in this direction and not in the opposite direction. So if we look into the curve or the characteristic of voltage of diode versus, the current across the diode voltage versus the voltage of the diode, what we can see is that as we supply voltage to the, so here is 0, as we supply positive voltage or in forward bias, I would say, in terms of diode, if we supply a positive voltage, what will happen is the voltage, there will be no current. So basically there will be no current circulating in the diode unless it achieves this VD0, right? This VD0. So this VD0 is just a model representing the real behavior. The real behavior is basically it will increase gradually. So in the middle here would be basically the bias voltage of either 0.7 or 0.3 depending on the semiconductor, right? This is the real curve, a more accurate curve, but usually in order to just model the diode just for utilization, we say that the current will cross the diode once it attain VD0, what we call bias voltage or cut-off voltage, right? So VD0, how much how much is VD0? VD0 is for silicium is between 0.6 and 0.7. Usually we just take the value of 0.7 volts. So here it is explained for VD equals to VD0. VD equals to VD0. Once we have VD equals to VD0, diode is on. Therefore, we have currents. Unlimited. So it is now a short circuit, unlimited, and very large amount of current circulating across that diode. But if we have VD smaller than VD0, the cutoff or the bias voltage, if it is smaller than the bias voltage, then the diode is off, right? So this is what we call the current voltage characteristic of a diode. So the important criteria that we want to remember for the analysis and utilization in the future slide is that VD0 will take equal to 0.7, and if it is larger than 0.7, it will conduct. Lower than 0.7, it will not conduct. If we go into a larger range of voltage, basically it's not just positive voltage. We can also go into a reverse bias region, negative voltage, right? So here, once it is on, this region is what we call forward bias region, where we have the diode functioning normally. If we supply the voltage in the opposite direction, in reverse bias region, what happens is the diode will not be switched on. It doesn't conduct any current. It may conduct a very small current, as what we call minority charges just now, but usually it is neglected as it is very small. But as we supply more and more current in the reverse bias region, we might fall into a condition where we will go beyond the depletion region. We will go beyond a certain. If we goes beyond a certain value of voltage, what will happen is what we call a reverse breakdown region. So we will completely goes across the depletion area, and the current will also, basically the diode is just broken and it just conduct electricity, and there's no opposition anymore to the current.